Okay, well guys, today is numbers and names number 12, number 12, and today we will talk about another applications and examples of mathematics, a little weird one, and probably you never heard about it. It is a math of invention. Regular logic does not allow us to invent anything. Logic is just going on the surface. It just gives you one thing, then derive from it another thing, but it's not new. Just confirming or proving something that we invented or suggested. If we did not suggest anything, so we don't know what will happen. But there's a method of invention actually, which was developing for some years before this day, for a few dozens of years already. And it began from so-called algorithm of invention, which was invented by a Russian inventor of German origin, Heinrich Altschuler. He was also a science fiction writer, pretty famous one, and he is considered like a Russian Edison. He had about 2,500 official patents registered.
Official what?
Inventions.
Oh.
Inventions. Officially registered inventions, 2,500. And so he gathered some years ago. He gathered a group of scientists and volunteers who worked on this. They research made a great research on about 40,000 inventions. Found the radical ones, and they found the ways how those inventions were done actually. And there's certain logic in it. So, and about this logic I would speak today. And this logic is definitely mathematical, generally speaking. Okay. So remember we were talking about the transformations of opposition. So again, symmetry, right?
Yeah.
Symmetry and the special symmetry which is called opposition. Or I use this word also, negation. We were talking about that if we have something that we call A, and we have everything else which is not A, this is the sign for negation. So something opposite to A, something inversed to A, right? So we have two things, and there is a border of it, right? And the border is called definition. This is the definition of A. But anyway, so if we have A, right, and we want to suggest something new, because what is invention? Invention is something new way to do some old thing, right? So we want to invent, like, for example, how to swim in a new way, right? And we know how the dogs swim, right? Like this, right? Dog type, right? So we want something new. So it's still old things, still swimming. So we still something have the same. And if something came the same, it is called, this transformation is called what? When we change something, but something is still the same, remains the same.
Symmetry.
Symmetry.
Yeah, symmetry. So this is symmetry. So invention is actually a symmetry. And the simplest symmetry is opposition. And opposition means we have something, some old way to do things, which we call A. A is something how we do. Regular thing. We look around, everybody does that. Like for example, they wash their hands in a certain way, or wash the floor in a certain way, right? Or wipe the floor in a certain way. We look at it and we say, okay, you're doing something maybe wrong. Maybe there should be something new. So, and something maybe more effective. There's a question actually, would it be more effective or not? But anyway, if we want to invent something new, so the first thing we should look for is negative A. Not A. something opposed to this, something inversed. How to find this thing? Because there are many things that is not A, right? You can suggest many things how to watch the floor, right? And yes, yeah.
Is a minus A technically still A because A is still kept?
Yes, still A means that it's the old thing, right?
Yeah.
So we're still washing the floor or somehow cleaning it, right? In some way. But we change something significant in it. So it's not the previous A, it's now new. So it has something remained, but lots of things are new. So this is the first thing, and it is pretty effective, as you will see pretty soon. We'll talk on this. But so by the way, the first rule of that found by Henrik Altschuler, right, for the inventions. The first rule: if you want to do something new, just make something opposite, inverse how you do the things in some way, and you will get an invention. This is the first and the most powerful idea in innovation. So this is this kind of transformation from A to not A.
Microscope.
Yeah, microscope, and opposite to it what?
Microscope.
To microscope. What is opposite to microscope? Microscope looks into small things. Huh?
Telescope.
Telescope, right. Look at big things. And they're actually almost the same construction, very similar. The optics is very similar, but you can use it both ways. So this is one of the things, right? Exactly. And if you think about it, you will find lots and lots. Now, what is the basis of all these things? Why can we use this simple rule, and there are other rules too, as a mathematics for invention? Like, how do we know that the thing would be more effective than it was before? Would it be a real invention, or would it be some fantasy? Okay, maybe it's interesting idea, but it's not like good, right? The main thing is when we go a little back and think about remember numbers, right? So we can count things. So we have a lot of similar trees, right? Remember?
Yeah.
A lot of similar planets, a lot of similar quanta, right? And lots of similar people, and we can count them because they are similar. So in a sort of way, abstractly, they are identical. The quanta are actually totally identical. So we know that this is a law of physics. They are indistinguishable between each other. So, but trees we can distinguish between two trees, but still we can count because we are abstract to something that is the same, right, in there. So why we can count the things? Because probably in nature we have something really underneath just our logic. Trees are really similar in some things, and if we look at it, really there's the stem, there are some leaves, right, the branches, this construction. Okay, so you understand what I'm talking about, right? The same thing with planets. They're round, they are in space, and blah 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 blah. So yes.
They're round and in space. That means round. That means round comets could also be planets. That we were saying.
No, we talk about planets. Planets are certain round things, right? It's not like asteroids. Asteroids are small and usually not round. They can have very weird looking forms, right? But planets are round mostly. So why we can do that? Definitely there is something in the nature, not in us, but in the nature that allows us to count these things. And if we look a little deeper, I think I mentioned already, we will find quite a few other things that are very, very basic in the nature. And those basic things, they are called, in philosophy, they are called universalia. Universalia. This is a Latin or something. So some universal things, right? So some universals is some identity in the nature that allows us to count things, right? Are there any other universalia? Yes, if we look into it, we'll see one of it is a very famous one. If somebody, just a sec, if somebody of you read Shakespeare, nobody?
No.
No, but Antosh, I hope Read at least something?
No.
No? I'm sorry about you. There's a famous thing called Hamlet. And again, in this famous play of famous writer Shakespeare, there's a mostly famous phrase that everybody knows, every cultural man. Hamlet says, to be
Or not to be.
or
That's
not
the
to be.
question.
That's the question, right? So this is the famous phrase. Okay, be or not to be. So, and this is actually the formulation, poetic formulation of one of universalia. This is universalia that anything in our world can be or not be.
Dida,
Uh-huh.
is universalia, it's, what's it called? Latin?
I think so, but I'm not sure. I didn't check it. Probably Latin, maybe Greek. Probably Latin. So, like sounds like Latin.
Huh.
So be and not be, right? So anything, if you look around and look like whatever, like imagine anything. Do you know anything that cannot be, or maybe not be? Anything?
First,
Hmm?
the universe.
Universe, yeah, it is. Looks like it's here, right? But it's
possible
very
for it not to
possible
be.
that it would be not here, right?
It's impossible for it not to be,
Why it's possible?
because that's all we know.
How do you know that? By the way, there are lots of philosophers that said that there's no actual universe. You know, like there's a pretty famous guy, bishop actually. He was bishop and philosopher. Bishop Berkeley. And Bishop Berkeley, he is famous by his very famous to postulate, right? He said that only I, so he, only I exist, nothing else.
Yeah, that's called solipsism.
Everything, yeah. Anyway, it's there's no way to actually to unprove it. There's a solipsism, yes, but we just don't like it. But it doesn't mean that it's unproved. Unfortunately, you cannot prove the real existence of the universe. So it exists or does not exist. That's very, it's a big question.
Exist? That's kind of a paradox.
Yeah, exactly.
Exactly.
Because
No. I think we found something that cannot not exist, Daddy.
yeah, because
Uh-huh.
if I,
It's the universe.
No, it can exist.
Yeah,
Just think about it.
well,
It's like a division by zero. I disagree.
Okay, division by zero, division.
Dita,
Yeah.
that bishop guy said that is a paradox.
Yeah.
Anyway,
Because if I say nobody else exists, just me, then you would say it for yourself. That means you didn't exist, but that means I don't. But I say I do exist.
but which one of us exists?
Exactly.
I think the guy was smart enough to understand that he's talking about paradox. He just don't put it in this way. That's all. He understood. He understood this paradox, yes, and everybody else understand that too. So, but anyway, so to be or not to be. Okay, universe. You may think about it. You may believe in it or not believe in it. But anything else? What is this? Oh, this is not. So anything else can be or not to be or not be. But if it's something is, oh, Jesus Christ! If something is, this is somebody knocking from other universe, you know. And there's a question: does it exist or not? Okay, so we have something that is not be and something that it is. It exists, right? We have a transition from not be to be, right? So from nothing to something. Nothing to something, nothing to something. And if we have this transition, this is opposition, of course, and this is symmetry, right? So transformation from nothing to something. First of all, we may notice, yeah,
Yeah, nothing to something is a paradox because anything you can say is something, so that means nothing.
Right.
Something is something. Me and Vita.
Right, Vita, right. Actually, even definition of nothing, like actually any definition. Remember, definition is about negation. So any definition For example, in the definition of nothing, it's actually negate itself, because nothing nothing exists, including nothing itself. So when you negate,
That means you can't put anything in that circle because there's none of it, but then it can't be on the outside because there's only, I don't know how many of nothing.
yep.
Because it's nothing.
Okay, but anyway, we have nothing, we have something, and we have some transformation, right? We have some transformation. Transformation, it is operation. Remember the name?
Yeah.
Operator, operation. Right? So some operation. So we have two objects, or whatever you call them, and operator between them, right? So like A to B, and this is operator A and B, right? And if you look at this, so there's nothing, so like something, and also operation. You can use this thing to anything around, like B and not B. There's a transformation from not B to B, and we call this usually. How can we call this? If something do not exist and then suddenly it jumps into existence.
In negation?
Negation, yes. This is like
Symmetry?
logical, but in normal life, something did not exist and then it
Okay.
appeared.
Oh, no, not it. Hold on,
Birth.
it's not it.
Birth. Birth.
Birth.
Yeah, birth. Actually, creation too. Whatever. There's some of these words. Yeah. So this is birth, right? So this operation we call birth. And if there's that transformation, there's transformation back, and this back transformation we would call death. Right. From B to not B. B or not to be, right? To be or not to be. Okay. So, and we have that everything around can be, cannot be, can be born, and can be dead. So appear and disappear, and all this around things. So at least these things are very, how you say, universal. So these things are all universalia. You can talk about anything in the universe, including universe itself, and everything has can be, cannot be, can be born, and can be dead. So can be destroyed, right?
Wait, so David, you're saying universalia?
Universalia, yeah.
You're saying universalia is a bunch of negations?
Yes, if you look at it, yes. But we will see it just a little later. Okay, so we're talking about these kind of transformations, right? So you see that everything is like that. In mathematics, if we have some objects, right? Some objects, the set of objects, right, which are transformed into another set of objects, and between these objects there are some relations like transformations. So this is A, this is B, this is C, right, and they can be transformed into each other. So sort of operations or operators.
They're all the same thing.
And those I prime, B prime, and C prime, that's not the same. If you image this set into some another set of another objects, A prime, B prime, C prime, and also we make the same transformation for the operators or transformations, right? So transformations are transformed to that kind of transformation. The whole thing in mathematics is called isomorphism. Isomorph. Isomorphism, yes, you're right. Isomorphism. So remember this thing, this is important. So we image not only objects, but also the relations between the objects. So like transformations, whatever.
Isomorphism.
And this means very important thing. If we have something universal, really, like universalia, right? So the objects are maybe A, maybe B, maybe C, whatever. They still have can be, cannot be, can be born, can be dead. These universal things, and we see the same thing in other objects, in each object in the universe, right? It is called isomorphism between all the objects in the universe. Yes, okay, question?
How do you realize that birth and death, that they're sort of related, yet they're complete opposites?
Of course, birth and death are complete opposites. B and not B are complete opposites. You see? Birth and death, it's the same. Not birth It is there.
Why can't you have birth without that?
So they opposite too. They all opposite. So yes, remember you said that universe is a bunch of negations. Exactly, yes. If we look at it, if you look that we saw how many universali we have actually, we have lots and lots and lots of them actually, and that allows us to model certain things very far from us, like physics in the universe, physics of the planets, physics of the stars, to model them by the names in mathematics and numbers. Mathematics, as it is, mathematics, the only existence of mathematics, it is possible because there are universalia. So we can use certain numbers and names like N or B or A, 1, 2, and everything to count everything: planets, stars, universes, people, whatever. And the same thing with other universalia: be, not be, birth, death, and everything else. Just understand that to understand the universality of mathematics. And if we understand it, if we take it into consideration that all these things are universal, when we talk about evolution, how did evolution? Evolution.
No, but disease.
We know actually, science tells us that everything is evolving, so everything is developing in time. And there are certain laws of this development. And the laws of this development, again, like evolution, is one of the universalia actually. Everything evolves. Whatever you look, like people grow up and they become smarter and they evolve, they get some skills and everything, right? The universe itself evolves from Big Bang to the particles, then to the clouds, then to atoms, molecules, then stars and everything else, right? And humans, blah blah blah, everything like this. Everything evolves. So this is universal. And the laws of evolution, how evolution actually works, those laws are universal too. And the main law of this evolution is that thing comes from not be to be. Big Bang, nothing, right? Then universe. Person, right? Nothing, then cell, then human, right? And everything like this. So this goes universally. The same thing, there are birth and death and all other things, by the way, we'll talk about them a little later. So this is universal. And if it is universal, we can talk about how technical things evolve. Like we look at the progress, which we call technical progress, or scientific, right? Technical scientific progress. Progress is evolution. And if we have everything evolving, so the same laws are used here. So if we have some technical solution for something, solution number one, right? And we want to find out where it will evolve, so this would be negation of this solution. Opposition, inverse. And this is the first law that was found by Henry Altshuler in real inventions. The most effective way of inventing things. So how people invent? They actually think about this. They look around and they see that everything evolves like this, and they apply it to the thing, and they get the thing which is next step in evolution, and it is invention. Think about it. So this is solution number 2. Okay. Now, so this is birth, right? And we can go a little further with this universality. Like we have birth, something to some nothing to something. And then after birth, right, birth is transformed by the same law. Birth is transformed into death, right? So it's nothing again. We can call this nothing number one. This is nothing number two.
Yeah.
Right?
What is the illusion giving birth to there?
Yeah, right. Allergy, guys, allergy. This is existence of allergy. He proves it. He proves it. He proves it right now.
Birth to a new universe.
It exists and thrive around in spring especially. So what do we have here? What do we have here? What is the process? What is the process actually? How can we call transformation from birth to death? This is birth, and this is like dying.
Negation.
Right? Huh?
This is negation.
Say it again?
Negation.
Negation? Yes, it's negation. It's everything is negation. We just found it, but this is very abstract. Just go a step further and just look.
That short embarrassing moment we call life.
Yeah, right. Antosha, you got it, guys? So
Yeah.
this is life of anything.
Very embarrassing short moment.
It's a universality. Life of anything, whatever. Planet has life, people has life, universe has life. Yes, from Big Bang to some say Big Crunch, or whatever other, or maybe thermal death. There are lots of different scenarios how this universe will end. Nobody knows for sure for now, but anyway, it will end somehow. So there is end. There is a beginning and there is the end of everything, and so we have the same process. So we can process image it like this, right? So birth and death, right? And if we try to use the same, go to opposition, the same thing to this, it will be what? Opposition to this process of life. So this is life, right?
Uh-huh.
So how we image this thing? So probably back, right?
Yeah.
From death to birth,
Rotting.
Oh, no.
like this. So we start from death and then birth. What can this be?
Death to birth?
Uh-huh.
But wait, how's that possible?
Right, how is this possible?
Oh wait, go to hell.
Oh, okay, yeah, somebody goes to hell, somebody to heaven, okay. Okay, you may talk like this, yeah.
Or some people believe that, like.
Okay, you know, okay, in the spring, in this,
You come back as a new
no, wait,
person.
we have grass in the spring, right? It grows up. At the end in the autumn, grass, what?
Guys,
Dies. What about next spring?
it goes back, but.
It goes
then
back, right, and very similar to before. It's different, of course, but very similar. So there is thing which is called revival or resurrection or whatever, right? And
from Harry Potter.
there is a process goes like on the background. Usually we don't see it, but it's there, right? It's a circulation of life. It goes everywhere. And by the way, because of this process, periodical process, right? We have what? We have many things here, you see, which we can count. 1, 2, 3, 4, 5, 6. So this process of resurrection, life of resurrection, is actually, because of this universality, we can count things and we come to like regular mathematics, like arithmetics, algebra, and whatever. So these things goes like this. Okay, now let's talk about some small examples of all this, and you can go further and further and further. Actually, there are some other things we will talk in short. So evolution makes the logic and mathematics of invention possible. Evolution of technology. Technology evolves, and we know the laws of this evolution. That's why we can predict certain things. There's actually a way. There's a mathematics under this. There's a way to form equations actually. So you may form an equation to invent something, and the equation, when you solve the equation using mathematical methods, it's not easy, but you can do it. you can get a sort of a more or less detailed description of new invention. You can do that. But it is a little, it's elaborated mathematical process, and there are certain easier things which Henry Schule suggested, actually, some easier for the humans to do things. So what he suggested, the first, of course, like, let's say, from A to go to negation of A, right? Inverse.
Yeah.
Inverse opposition, right? Then, remember, there are certain things which is called life, or in normal, like, physical term, it is time. Time.
Uh-huh.
Everything time is timely, right? So time is beginning and end.
You have to live.
Opposite to this is, of course, it's anti-time, right? It's anti-time, or preservation, resurrection, whatever you call. But actually, if we saw around anti-time, it is space. Everything that we see in space, it's what existed before. Nothing that we see actually exists now. Everything everything is in the past. Everything that we can measure or see around us, even our hand, it is in the past. It's not in the present
You told me
time.
about this.
Yeah.
It takes a certain time for light to get to our eyes and through the optic nerve to our brain.
Mm-hmm.
So from Proxima Centauri, we see it from like 700 million years ago.
Right. Right.
That much.
Right. So it is definitely, space is very close to what we call anti-time, something that existed, and we see it. So the second law of that Schule found that went from inverse form to timely form, timely, or maybe pulse, right? Instant, something like this. So instead of what you did before, go to do it in pulse, instant. Like, for example, if you're using hammer, you do exactly that. You just use hammer to hammer the nail, right? And interesting enough, that if it's very very important that you do it like really instant. If you do it slowly, the nail will break or will be curved. You should do it fast, very fast. So another thing is anti-time. It's anti-timely, right? Something that may continue. Something continues. Continuous, right? The simplest thing is just don't do anything. Just wait. Yeah. Maybe it will solve itself. The problem may solve itself. Oh, how's it? Sleep over, right?
Exactly. You wait to die.
Yeah, you might do it. Yeah, why not? If you want to sleep all your life. Anyway, right. Then the next thing is, because there are those circles of life and death, they go up another. There are many of them, right? They will have one too many. So if you have in your solution, you have one, something that is single, divide it into many. It is called by Henry Schule, it was called like many little men. He suggested, just think about lots of little men which can do your work for you.
I wouldn't really feel too good because I would feel sorry for them. I know, because they're tiny little things.
And of course opposite. If you have something that you use many things, right? In something you have many things, just go to one. You can do this or that. So they always goes into opposite. So how it works actually for A and not A. The examples you suggested, one example, right? I already forgot it, but Vita suggested, right? From negation, with negation, right? Some inventions. One of that I actually like is that. You know how Icebreaker works?
Uh-huh. No. Well, no, not really, actually.
We have ice, right? Which is floating on the water, right?
Uh-huh.
And their icebreaker has nose like this. It is very heavy. Icebreaker is heavy. and it moves here, and it goes over the ice, and then with all of the weight, breaks it. It's called icebreaker. It's not cutting the ice. It's going on the ice and then break it by its weight, like this.
Oh wow.
Okay.
Out of it, what's the material of the icebreaker?
Well, there's a very hard. This is steel, right? There's a very hard material here, so they use this. This is the idea of icebreaker. Now, if you go to something negative, right? So, what's the negative idea to the icebreaker? What do you suggest?
Ice maker.
Huh?
An ice maker.
Ice maker, yeah, that's a good thing. But you need to break ice. If you make ice, I'm not sure how you. Maybe you can think about it. Just it doesn't come to my mind.
Oh, there's an ice fixer.
No, instead of going on the top, where can it go? What's the opposite of
On
the
the
top?
bottom. It can go to the bottom.
Okay, just inverse, like reflection, right?
Receiver.
Yeah, that's what Katya suggested.
Oh, great, Katya.
Ice
That's a good
maker.
idea. So that's a good idea. By the way, it was counted, actually. It was calculated, and it found out that this way is about 1.5 more effective than the current way. That gives 50% more, save 50% more energy than this one. So this is much more effective. You can use, instead of icebreaker, you can use like a submarine, which goes submerged on ice and break it by moving it up, not down. Icebreaker moves ice down, but there's water which prevents for ice to go down, right? It's floating on the water, so it's difficult to really put ice down. So it's difficult for the icebreaker to do. But when you go like under the ice and push it up, there is just air around, right? It's very easy to break it. So it's a very much great saving on this. And this is a real patent, actually. This is patented as an invention, and very effective ones. They don't use it because it's a little, technologically maybe not easy for them to do right now, but it's much more effective than breaking the ice. Now, for other ideas like timely, we talk about it, right? So if you have a nail and you want to put a nail into the wood, right? You cannot press the nail. You can press this these things. How we call these things when we put them? Oh, forgot.
It's a hammer.
Clips?
Yeah, clips. Скрепки эти самые, как
Paper
кнопки.
clip.
Yeah, paper clips. Yeah. So the paper clip is not long, right? So we can press it, just press it slowly, and it goes into the. But the nail is long and thin, and if you try to press on it, it will curve immediately, and you will fail. So the way how you do it, you use hammer timely as a pulse. You just hit it very hard, hit it very hard and fast. And if you do it, you can do it even from one strike. The professional carpenters. They can move nails like this with one strike, one hit of the hammer, bam, and that kind of nail goes into the wood.
Oh my god.
Yeah. By the way, I used to do it when I was a student. I was trained to do it.
What?
So, so it's very interesting way. So the same thing continues. We can say weight, maybe whatever, or something else. One to many. Very interesting way. There's a process which is called stamping, I think.
What, stamping?
Yeah, like if you have a sheet of like metal, right?
Yeah.
Sheet of metal, and you have something which is called actually matrix, but I'm not sure how in English it is. I think it's matrix. So this hard metal things which form like of this, right? Something like a pit, right?
Uh-huh.
A pit. And then you have another thing here which is called Poisson's stamp. Poisson's stamp. Again, heavy thing which hit this sheet of metal into this hole, like this. Bam, stamping. You probably saw it somewhere. Stamping. And so this the sheet of paper will have this form then. So to create thing from metal like this, right? You do this thing. You get a flat sheet of metal, then this stump, and the matrix down there. You got the idea? Like pen, and it's done, right? Another pen, another thing. They're stamping. They're multiple stamping. There's a problem with this stamping. This thing is getting used very fast. What's the name? What's the term for this?
Out?
Huh?
Worn out?
Yeah, worn out, used up. Yeah. So worn out very fast because the metal, metal is just metal, right? So and it is expensive to change. So what was the idea? Come from one thing, one stamp, to the multiple, many little men. So what the idea was? It is actually patent too. What the idea was very interesting. You get metal. What's the name for this? No. I'm sorry, just a sec. Like sawdust, but metal. Fillings. You know what sawdust means, right?
Yeah.
So something like this, metal sawdust, and a magnet. A strong magnet, right? So you put here this sawdust here, and then bring a magnet, strong magnet here. And when you take it out, you will have the whole thing, but made out of metal filling, made of sawdust, attached to the magnet.
But I have a question.
Yeah.
If you take the magnet away, all the sawdust will fall. So how do you keep it together the whole time?
No. Interesting thing that is not. If the magnetic field is strong enough, they are so close together that they become really hard. So hard that it can be used like a stamp, and it's never worn out because it's easy to get it back. It's just.
Oh, is it like this? They're combined because they're really close, so the electrons can pass through, making it. And I'm not joking. Impossible to rip off.
What?
Is it like they're very close, so the electrons can pass through each sawdust, combining it, making it almost impossible to rip it off.
Oh yeah. Oh yes. You're calling this. Yes, looks like this. Yes, right. Probably. By the way, yeah, you're right. The physics of this thing is very close. Not only electrons, the atoms, if they're in BAC, it's a Bose condensate, right? Actually, they may be formed in a special form, like a funnel. I told you, like there's some sort of a swirls, right? Swirls of funnels, or even hard things, and they does not change by time. Yes, they're very stable. So it's very close. Yeah, in physics, it looks like this. Yes, in the fillings in this sawdust thing. The physics of this is that when you apply the strong magnetic field, right? Strong magnetic field here, they press to each other so strongly that the friction between them do not allow them to go anywhere. Those they are compressed so strongly by the field, so the friction does not allow them to go anywhere. So it's become a very usable stamp. So this is one how it done another way, this way. The other idea of there are many things, like for example to wash, like there's idea to wash clothes by creation a lot of bubbles into the water. No chemistry, no nothing, no chemistry, but you create lots of bubbles, and those bubbles, when they are collapsing, they produce a very high pressure and they clean the clothes, believe it or not.
Really?
Yes. So and the thing is that this way of washing machine, right? It's just a bucket with water, Nothing, no chemicals, no nothing. But you put special thing which gives, this is called ultrasound. You know what ultrasound means, right?
Why would they need that in there?
You know what ultrasound means?
Yeah.
This is the sound of the frequency that we cannot hear. Like dogs can hear it sometimes, but we cannot. So this ultrasound produces lots of bubbles in the water. And if you put clothes become very fast clean. Also, it's become very, very fast word out too. But so this is a bad sign of this. But anyway, you can clean clothes with this way without any chemistry. And there are many other things. So that's it. This is an example how symmetry and maybe used like even in such far thing. What do you think? Maybe not mathematics, but it is exact mathematics. I will show you mathematics of invention. And no questions, guys.
No.
No, you have all the questions. Okay, so I have questions for you guys. So try to invent something using one of these ideas. Okay.
Invent something?
Yeah, like for example, first, invent new type of windshield cleaning for a car. Maybe 3 types, some of them.
You get the loose to blow on it.
Yeah, okay, you can, okay. Okay, the second question. Again, new type of, I have, okay, new type of washing, okay, not this that you suggested, but new type of washing machine. For clothes or maybe for the floor, whatever you want to. And the third is, again, invent new type of flying.
Oh, no. This is going to be hard.
No, it's not hard. Just use that and then think. Like so-called brainstorming, right? Just think about opposite, right? Inverse. And make your fantasy fly. And you will find out pretty impressive ideas, I assure you. Okay?
Interestingly, all 3 of these can be solved with the loosest blowing in the hard.
Okay, stop it, Antosha. Okay, thank you guys. See you next time. You want to talk to Babu or not?